Today we'll be discussing a new topic in supramolecular chemistry where we'll be actually looking at a combination topic which actually became important in the field of supramolecular chemistry because there were a lot of developments which were happening in molecular biology where large number of structures were being determined. For example, protein structures, peptides and viruses structures were being determined, and on the other hand the chemistry was also growing tremendously at a very fast pace because organic molecules, different kind of organic synthesis, total synthesis and different kinds of chemistry, organometallic catalysis, all these fields were developing. But what was important is supramolecular chemistry came in between or bridges both these fields, where we take the knowledge from chemistry to make new building blocks, and then we want to model the processes which happen in life. So the synergy between chemistry and biology became very important, and biology is more complex in the sense there are large number of constituents, different type of constituents having specific functionality, and where the shape, size, molecular weight, all these plays a very important role. Chemists are more interested to make new molecules which have got a defined set of functional groups. For example, the focus by and large has been to design and make new organic molecules which involve total synthesis, for example, of natural products. Today the focus is on areas like CH activation, where new catalysts are being developed to introduce specific functionalities on the organic scaffold. But then there is supramolecular chemistry actually is a very interesting area. Now that you have heard about so many lectures in this course, you now realize the potential of this area. That what is the purpose of learning chemistry? The purpose of learning chemistry is to understand the origin of life, as to why life exists on earth, how did life originate on earth, how did the small specific set of atoms start combining to form molecules, and then how did these molecules form larger molecules and eventually proteins, which are enzymes, which are actually the workhorses of cells and biological function. So and then we also have the important theory of Darwin, which talks about the evolution which happened in biology, and therefore the idea was that instead of trying to make specific molecules only with predefined targets, is it possible to make an array of molecules which can also reversibly dissociate and then form and then again associate to make different kind of molecules which have got a specific function. For example, we have got an enzyme and we would like a certain ligand to inhibit the activity of that particular enzyme. Now that ligand which has got the best steric and electronic fit with a specific portion of the enzyme is what is going to give you the desired activity. And as we have already realized that there is a competition between kinetics and thermodynamics. Life is actually an example of non-equilibrium thermodynamics. It's more like the dynamical processes at play, because if thermodynamics were to rule, then the end product is essentially carbon dioxide and water. But we know life still exists. That means there are non-equilibrium processes at play which sustain life on Earth. So it's so the question which was asked by supramolecular chemistry is that can we design ligands in a specific way by creating a pool or a library of molecules which will not be present initially in the process of identifying the potent ligand which will best fit with the enzyme, but which can be created instantaneously by suitable combination of or suitable combinations of chemicals to give you the constituents which actually specifically dock or interact with a protein, and that leads to the amplification of the process of molecular recognition. And this entire discussion which I have presented to you was actually propelled by Professor Jean-Marie Le, and it gave rise to the foundation of systems chemistry. So just to give you a couple of salient features about systems chemistry, it is a union of supramolecular chemistry and prebiotic chemistry with theoretical biology and research on complex systems to address problems related to origin of life and the search for a deeper understanding of structural and dynamic prerequisites leading to chemical self-replication and self-reproduction. And third, which is of most relevance to systems chemistry, is the chiral symmetry, the chiral systems, where we have the chiral symmetry breaking in nature. Because when life started on earth, there was a specific chirality which was being utilized to create the molecules of biological and chemical interest. So what is the origin of chirality? Because in principle we have both the chiral forms, but it is one of the chiral form which is utilized for making molecules that support life on earth. So life is, as we know, so what are the implications of these concepts is that we would like to understand origin of life, and life is based on homochirality. And the interesting thing is that when these homochiral molecules were being designed or synthesized, they were done without any chiral environment. Okay, so that is the interesting thing. So, and the utilization of one kind of chiral handedness that emerged without any chiral environment. So this is what is intriguing, this is what is puzzling, that now how did this process happen? Because we actually know that today synthetically, if you would like to make a specific chiral enantiomer, then you have to induce the necessary chirality into the system. For example, if you want to have enantioselectivity, it can only result from the chiral information which is residing in the system. For example, you have to make the catalyst or one of the reagents or one of the reactants which has to be chiral. So the chirality or that information about the chirality has to be coded or prescribed within the system. It has to be stored as a memory in the system, and then only it can lead to enantioinduction or enantioselectivity in a chemical reaction. And when you are going to do these chemical reactions in the laboratory, unless you have the chiral information, the outcome of a reaction will form a racemate. That is, when you do a chemical reaction in the absence of chiral information, it will create a racemate 50% is to 50% distribution of enantiomers. So these are some of the challenging problems which systems chemistry would like to address, and we would now like to explore some of the aspects of the systems chemistry and how it all became very relevant. So now there is a merging ground, as I told you. We have a vast chemical knowledge from chemical structures, and we have knowledge about different forms of life. So, can we have a synergy between these two areas where we will combination of these two areas, and that can give rise to the interface, because today science is highly interdisciplinary and people are working at the interfaces of physics, chemistry, physics and biology, chemistry and biology. So, this will give rise to the fascinating area of chemistry of systems chemistry or systems biology, where supramolecular chemistry is going to play a very important role in combining these two areas. And to achieve this particular process, what has been developed is actually the principle of what has been actually developed is the concept of constitutional dynamic chemistry, which we call as CDC. We can also call it as dynamic combinatorial chemistry, DCC. That is how it is being addressed today, but initially when it was proposed by Professor Jean-Marie Le, we started with the concept of constitutional dynamic chemistry. So, we are able to make certain bonds by reacting certain functional groups, and we make certain molecules. And if during the process of molecular recognition, we would like to now change this particular molecule which binds, then this formed molecule has to dissociate into the starting components, and then again we will have to have different components, and then we will have to have the suitable combinations, so that we get the desired constitution of that molecule which best fits with the target of interest, and the one where this fitting is the best tends to get amplified or gets more well recognized with the system of interest. So, this concept of constitutional dynamic chemistry became very important, and this can be divided into two parts: molecular, that is the dynamic covalent chemistry, and the supramolecular, that is the dynamic non-covalent chemistry. This, if we want to exercise the dynamic covalent chemistry, we will have to utilize the knowledge of reversible covalent reactions, and this will involve the reversibility of non-covalent interactions. So, when certain interactions form, you can again reversibly dissociate back into the starting materials utilizing this concept of non-covalent interactions, thereby creating the dynamic non-covalent chemistry. And this is important because selectivity is important in chemistry, because we have to identify or select molecules which satisfy a specific function of interest. And the fact that non-equilibrium electrochemistry is very important was actually recognized way back in 1861, when the Formose reaction was proposed by Butler-Roth. And Butler-Roth in 1861, he proposed the mechanism of formation of sugars from formaldehyde, which forms glycoaldehyde, and then the higher aldoses and ketosis. And this Formose reaction takes place under alkaline conditions, and in the presence of minerals like calcium and barium. And when this process happens, it is actually creating a library of molecules which are interconverting into the higher aldoses and ketoses. So during this process of Hormuz reaction, already the library is being created by the nature, and then these libraries can then combine to give the higher sugar molecules which have got higher molecular weights. So, the process of this dynamic combinatorial chemistry essentially constitutes a network of organic reactions forming oligomers, either linear or cyclic, of varying size and composition. Okay, so this is the basis of dynamic combinatorial chemistry. Now let us look at this overall sequence of events as to what we are trying to do by the synthesis or the creation of this library of molecules. And now we have the components to start with. We have the components here. For example, we have a square, we have a pentagon, we have this particular shape, and we have this particular shape. Now there is a selection. This is the equilibrium process. There is a library, selection. So we can have different kinds of combinations here. So we can have combination of this, this, and this to give this particular product. We can have this one, and this one, and this one. We can have this one combining with this one and this one. So these are the constituents. These are the components. These are the constituents. The constituents have been formed by combination of the different components, and then we can have thermodynamic pathways, and here we can have a receptor. Now say the receptor has got this particular shape. So this is my receptor, and I can actually have a thermodynamic selection, or I can have a kinetic selection, where, for example, depending on the shape of this particular cavity, so as you can see, what will fit in here is this so this particular molecule fits into this particular cavity. So this is the lock, and this is the key. So lock and key fit, and this process can take place by thermodynamic as well as by kinetic procedures. Now the most important thing is that there are different steps now in this process. So we saw the step 1 is a dynamic library of keys generated reversibly associated fragments. So these are the components, the fragments, and there is a reversible process which is operating, which is forming these constituents, and at any moment the reversible dissociation can take place, and then the components can again combine to give the constituents. This is the first step. And the second step, which is very important, is that the receptor, which is also the lock, it amplifies now or favors, this is important, the expression of that key or constituent that binds best to it, that is thermodynamics or that forms fastest with it, that is kinetics. So, all this knowledge of supramolecular chemistry is very useful to create these constituents, and what is important is that it is not necessary that all these constituents of the library have to be present at the same time. Depending upon what is the requirements of the key to fit into the lock, this active molecules can be generated at the time of requirement of the steric process. So, this library or the keys do not have to be formed before the addition of receptor or the lock, because once you identify the receptor or the lock, then these constituents can now again go back to the components and again form new constituents, identifying what kind of the steric or the electronic requirements is there to bind with the lock. So, before the addition of receptor lock, these libraries or keys will not be present, and this illustrating the notion of virtual dynamic combinatorial library. We call it as VDCL, sometimes we can also call it virtual dynamic library. So, now this very important concept of a virtual library comes into place, which is not really virtual in the true sense. It is virtual by means of the fact that it is not necessary that these keys have to be or the constituents have to be present, and as I mentioned that once we identify what is the best fit for this lock, then the system can actually prepare by a series of reversible dissociation and then association processes the right molecule which will now specifically bind with the target, and that will lead to the amplification of the signal or the response, and therefore we are able to identify the very key substrates which can bind with the receptors of interest. So, this is the philosophy behind the concept of virtual dynamic combinatorial library or the combinatorial chemistry which we are talking about. So, and then there are different kinds of bonds which are actually involved in this process. So, we can look at reversible covalent bond formation by different process. For example, by different processes or chemical reactions. For example, we have the carbonyl and we have the RNH2. It can reversibly associate to form the imine. We have the formation of hemiketal. So, this can reversibly form OR. Then we have aldol reaction which can form the aldol disulfide bonds which can form disulfide linkages. Diels-Alder reaction which can between a diene and a dienophile which will give the cycloaddition product. So, we can have these kind of reversible covalent bond formation. We can also have reversible interactions. For example, we can have N plus LM to give you LM N plus. We can have RCO2 minus hydrogen bonded with a amine group. We can have donor acceptor interactions to give you the donor acceptor adducts, and this can be further combined with reversible processes. For example, we can have cis trans isomerization, we can have bond rotation, and so on and so forth. So, these are the dynamic processes which are involved in the creation of the virtual molecular and supramolecular CLs. Virtual molecular and supramolecular combinatorial libraries can be actually created via the wealth of information derived from reversible covalent bond formation, reversible interactions, and the reversible processes which are at play. This is just a snapshot of some of the most important processes which operate. So, in the next lecture, we will take up some specific examples which demonstrate the applications of this virtual library as well as the combinatorial chemistry in action. Thank you.